Commutation methods in thyristors. Commutation is nothing but the turn-off method of SCR. It is one method used to bring SCR or thyristor from on state to off state. We can easily bring the SCR or thyristor into conduction state, but it is very difficult to bring the thyristor or SCR into off state. Thus, it is very much important to study the methods required to bring the thyristors or SCR into off state, that are nothing but commutation methods. We know that an SCR can be activated by using gate signal towards an SCR when it is forwarding bias. That is nothing but when we apply a positive gate pulse, SCR starts to conduct. But SCR needs to turn off when required for power controlling, otherwise power conditioning. So in order to control the power flow in the system, it is essential to control the turn on and turn off of thyristor or SCR. When an SCR moves in the mode of forwarding conduction, then its gate terminal loses its control. For that, some additional circuit should be used to turn off the thyristor or SCRs. So, this additional circuit is nothing but called as commutation circuit. So, the circuit used to turn off the thyristor or SCR are called as commutation circuits. So, this term is mainly used for transferring the current from one end to another. The circuit of commutation mainly reduces forward current to zero to turn off the thyristor. Thus, the forward current should be brought to zero, then and then only your thyristor or SCR can be brought into off state. So, in order to bring the thyristors to off state, the following conditions should be satisfied. The conditions are: first, the forward current of thyristor or SCR should be decreased to zero, otherwise under the holding current level. That means it should be hold, because when the SCR or thyristors are in forward bias, large current flows from anode to cathode. Thus, the current should be limited, and in thyristor just we can limit the current by using the resistance. So in order to bring the thyristors or SCRs to off state, we must bring the current, or we should control the large forward current and should bring that current into holding state. Otherwise, it is very it is very difficult to bring the thyristors to off state. That means we should control the forward current by adding the resistances, or should by bringing that current into holding state. Second, an ample reverse voltage should be provided across thyristor or SCR to recover its forward blocking condition. That means negative voltage should be applied across the gate terminal. Then and then only we can bring the current to zero and bring the thyristor or SCR to the off state. Once SCR is turned off by decreasing forward current to zero, then there exists surplus charge carrier within different layers. To recover the forward blocking condition of thyristor, these surplus charges should be recombined. So, this recombination method can speed up by applying a reverse voltage across the thyristor. So, when we apply or when we bring the forward current to zero, the SCR is turned off, but while doing this, so there is large change in the carriers between the junction, and we should recombine these carriers by applying the reverse voltage across the thyristor, and finally we can bring the thyristor or SCR to the off state. So this is nothing but the commutation of thyristor or SCR. Now we'll see what are the different commutation methods used in thyristors. The commutation techniques of thyristors can be classified into two main categories. First, natural commutation, and second, forced commutation. We'll see what is meant by natural and forced commutation. Natural commutation. Generally, if we consider AC supply, the current will flow through zero crossing line while going from positive peak to negative peak. That is nothing but if you consider any AC quantities, whether it might be voltage or current, it has natural zero crossing point. So if you consider one complete cycle, at in one complete cycle we get 2 points at which voltage and current naturally goes to zero, that is at pi and 2 pi terminal intervals the current and voltage naturally goes to zero. That is nothing but it crosses the zero line while going from positive peak to negative peak. Thus, a reverse voltage will appear across device simultaneously, which will turn off thyristors negatively. That means when the voltage goes from positive half cycle to negative half cycle, during this negative half cycle, naturally the negative voltage will appear across the thyristors, and thus due to a reverse voltage, the thyristors may be turned off immediately. This process is called natural commutation, as thyristor is turned off naturally without using any external components or circuit or supply for commutation purposes. Natural commutation can be observed in AC voltage controllers, phase control rectifiers, and cycloconverters. So these are the examples of natural commutation methods. Force commutation. The thyristor can be turned off by reverse biasing the SCR, or by using active or passive components, that is resistance, inductance, and capacitance. We can use this component for reverse biasing the SCR. Thyristor current can be reduced to a value below the value of holding current using this active or passive components. Since a thyristor is turned off forcibly, it is termed as forced commutation process. The basic electronics and electrical components such as inductance and capacitance are usually used as commutating elements for commutation purposes. That is nothing but the passive component inductance and capacitance are used for reverse biasing the SCR forcibly. Forced commutation can be observed by using DC supply, hence it is also called as DC commutation. The external circuit used for forced commutation process is called as commutation circuit, and the elements used in the circuits are called as commutating elements. Now we'll see the classification of forced commutation. We have 6 classifications of forced commutation method. Class A is called as self-commutated by resonating load. Class B, self-commutated by LC circuit. Class C, called as C or LC switched by another load carrying SCR. Class D, C or LC switched by an auxiliary SCR. Class E, an external pulse source for commutation. And class F is called as AC line commutation. Now we'll see this classification one by one. Class A commutation, called as self-commutated by resonating load. Figure on the right hand side shows the circuit connection for Class A commutation method. Class A is one of the frequently used thyristor commutation techniques. If the thyristor is triggered or turned on, then anode current will flow by charging capacitor C with dot as positive. So when SCR is forward bias, the current will flow through inductor and will charge the capacitor, and the dot indicates that it is a positive. The second order underdamped circuit is formed by inductor or AC resistor, capacitor and resistor. So L, C, R forms the second order underdamped circuit. If the current builds up through SCR and completes the half cycle, then the inductor current will flow through SCR in reverse direction, which will turn off the current. So after half cycle, the current starts flowing through the inductor, and when it starts flowing through the inductor, it is reverse bias, or it will flow through in reverse direction of that of SCR, and hence the SCR will be turned off. After the thyristor commutation or turning off the thyristor, the capacitor will start discharging from its peak value through resistor in an exponential manner. The thyristor will be in reverse bias condition until capacitor voltage returns to supply voltage level. So, as soon as the current flows in reverse direction, then the SCR will be turned off, and when SCR is turned off, the capacitor which was charged earlier when SCR was in forward bias mode, now this capacitor starts to discharge, and it starts to discharge through resistor R connected across the capacitor, and the thyristor will remain in reverse bias mode until the capacitor is discharged up to a supply voltage level. Second, class B, that is self-commutated by LC circuit. So this is the circuit diagram on the right hand side. The major difference between class A and class B thyristor commutation methods is that LC is connected in series with the thyristor in class A, whereas LC circuit is connected in parallel in class B method. Before triggering on this SCR, the capacitor is charged up, that is the positive or the dot indicates it is charged to a positive level. If the SCR is triggered or given a triggering pulse by giving the gate pulse to the by giving the pulses to the gate, then SCR will get triggered. Then the resulting current has two components: the constant load current flowing through RL load is ensured by large reactance connected in series with the load, which is clamped with freewheeling diode. If sinusoidal current flows through resonant LC circuit, then capacitor is charged up with dot as negative at the end of half cycle. So when during positive half cycle, the capacitor is charged to a dot of positive level, and during negative half cycle, when the resonance circuit LC is charged or the current flows through resonance circuit LC, then the capacitor is charged with dot as negative at the end of half cycle. The total current flowing through SCR becomes 0 with reverse current flowing through SCR opposing the load current for a small fraction of the negative swing. If resonant circuit current or reverse current becomes greater than load current, then SCR will be turned off. So, during half cycle, when the current flows through LC resonance circuit, the capacitor is charged in negative half cycle, and when it is charged in negative part, the current becomes reverse, and due to this reverse current, the SCR is turned off. Class C, that is C or LC switched by another load carrying SCR. So figure shows the connection of class C commutation method. In this thyristor commutation method, we observe only one SCR, but in this class C commutation techniques of thyristor, there will be two SCR. That means in class A and B, there were only one SCR, but in class C, we have two SCRs as shown in figure. One SCR is considered as main thyristor and other is considered as auxiliary thyristor T1 and T2. In this classification, both may act as main SCRs carrying load current and they can be designed with 4 SCRs with load across the capacitor by using current source for supplying an integral converter. So instead of 2 SCRs, we can also use 4 SCRs in class C. If thyristor T2 is triggered, then capacitor will be charged up. If thyristor T1 is triggered, then capacitor will discharge and this discharge current of C will oppose the flow of load current in T2 as the capacitor is switched across T2 via T1. So when T2 is turned on, capacitor will be getting charged and when T1 is turned on, capacitor will get discharged. Next type of classification is class D, that is LC or switched by an auxiliary SCR. So figure on the right hand shows the circuit connection of class D commutation method. The class C and class D thyristor commutation method can be differentiated with the load currents in class D. Only one of the SCR will carry load current while other acts as auxiliary thyristors, whereas in class C both SCRs carries load current. So the difference between class C and class D are class C and class D has two thyristors each, whereas in class C the load current is carried by both the SCRs, but in class D the load current is carried only by one SCR each or only by one SCR, not by two SCRs. The auxiliary thyristors consist of resistor in its anode which is having a resistance of approximately 10 times the load resistance. And we know that as we increase the resistance, current will not flow through that SCR or thyristors. By triggering TA, that is auxiliary thyristor, the capacitor is charged up to supply voltage and then TA will be turned off. The extra voltage, if any, due to substantial inductance in the input lines will be discharged through diodes, inductor and load circuit. If TM, that is main thyristor, is triggered, then the current will flow in two paths, that is commutating current will flow through capacitor C, main thyristor Tm, inductor L and freewheeling diode D path, and load current will flow through the load. If the charge on capacitor is reversed and held at a level using the diode, and if the auxiliary thyristor, that is TA, is re-triggered, then voltage across the capacitor will appear across main thyristor via auxiliary thyristor TA. Thus, the main thyristor, that is Tm, will be turned off. Next type of classification is class E, that is external pulse source for commutation. Figure on the right hand shows the circuit connection for class E commutation method. For class E thyristor commutation techniques, a transformer cannot saturate as it has sufficient ion and air gap and capable to carry load current with small voltage drop compared with the supply voltage. If thyristor T is triggered, then current will flow through load and pulse transformer. So when SCR is turned on by applying a positive gate pulse, the current will flow through the load and the transformer, that is pulse transformer. An external pulse generator is used to generate positive pulse which is supplied to cathode of the thyristor through pulse transformer. The capacitor is charged around 1 volt and is considered to have zero impedance for turn of pulse duration. The voltage across the thyristor is reversed by the pulse from electrical transformer which supplies reverse recovery current, and for the required turn of time it holds the negative voltage. That means by using a pulse transformer, the voltage is applied across the cathode of thyristor. That means a reverse voltage is applied by using the electrical transformer and it supplies reverse recovery current required for the off time. Last classification is class F, that is AC line commutated. Figure on the right hand side shows the circuit connection of class F commutation. In class F thyristor commutation techniques, an alternating voltage is used for supply, and during positive half cycle this supply of this supply the load current will flow. If load is highly inductive, then current will remain until the energy stored in inductive load is dissipated. During negative half cycle, as load current becomes zero, then thyristor will be turned off. That is nothing but when positive half cycle, inductor will be charged and the current will start flowing through the inductor until and unless there is energy getting stored into the inductor, and during negative half cycle the energy will be dissipated and the load current becomes zero, and then thyristor will be turned off. If voltage exists for a period of the rated turn off time of the device, then negative polarity of voltage across outgoing thyristor will turn it off. Here, the duration of half cycle must be greater than the turn off time of the thyristor. This commutation process is similar to the concept of three-phase converter. So let us consider primarily T1 and T11 are conducting with triggering of converter which is equal to 60 degrees and is operating in continuous conducting mode with highly inductive load. If thyristor T2 and T22 are triggered, then instantaneously the current through incoming device will not rise to the load current level. If the current through the incoming thyristor reaches the load current level, then commutation process of outgoing thyristors will be initiated. This reverse biasing voltage of thyristor should be continued until forward blocking state is reached.